Hello friends, good afternoon and welcome to the EduSat network. Our topic of discussion today is part of our ongoing series on operations management, and today the discussion shall specifically be on product design. And for this very lecture and discussion, we have this in our studio, same subject expert who has been part of this ongoing series with us, Dr. Subhash Kakkar.
Hello.
Director of a well-known institute in Delhi, and with this I request sir to begin our today's lecture. Thank you for coming.
Hello viewers. Today's lecture is on product design. This lecture is part of the series on operations management. We have covered a lot of subjects, lot of topics in this series, and today we shall be devoting time to understand the product design, and which is an important issue to be taken care of in a manufacturing industry as well as in service industry. In both manufacturing and service, we sell the products, and how to design the product we shall be discussing today, the complete process in detail. Today's topics will be concurrent engineering, QFD, design for manufacturing and design for assembly. Concurrent engineering, doing everything simultaneously. Whatever is required in design of the product, what all functions are required in designing the product, they work together simultaneously, parallelly, and time of launching a new product is saved. Next topic will be QFD, quality function deployment. This is also a technique for launching a product and deciding the features to be incorporated in the new product or changing the features of an existing product. And this is also known as house of quality. And then we shall be discussing design for manufacturing. Our design should be such that it should be easy to manufacture, and all the features which are required to make it easy to manufacture we shall be discussing today. And design for assembly also will be discussed today. All the features which should be incorporated in the product to make it easy to assemble will be discussed today. Concurrent engineering and QFD, both are similar expressions, and we shall be devoting time to discuss about concurrent engineering and its meaning. Concurrent engineering is a strategy where all the tasks involved in the product development are done parallel, and they are done simultaneously, and we don't wait for one function to complete its part of the job and it goes to the next functional area, but all the functional areas will work together and simultaneously they will come up with a new product and its design. Collaboration between all individuals, groups and departments within a company, and the departments which are to function together are customer research, designers, marketing, accounting, engineering. All these departments work together parallelly, simultaneously to develop the product. And this process is shown in this diagram. Commercial design starts with idea generation. Idea is generated through different sources, and these are competitors, suppliers, R&D department of the company, customers, marketing department, and the product or service concept is introduced, and this is known as idea generation. Idea or the concept is generated at this stage, and all these people work together. A feasibility study is made and performance specifications are decided. After these, three functional come into picture: form design, functional design and production design. When we discuss form design, revising and testing prototypes. When we discuss functional design, design specifications are generated. Under production design, manufacturing specifications are generated, and we come up with a preliminary design of the product. A pilot run and final tests are carried out on the product, and final design and the process plans are made, and finally the product is launched in the market. And this is a linear process, but when they work together, it becomes a concurrent engineering process. And now we will concentrate on idea generation. Idea generation is done through various sources: competitors, suppliers, R&D, customers, and the marketing department give idea regarding the product, and product or service concept is generated. And techniques used are perceptual mapping, benchmarking, and reverse engineering. Perceptual mapping is mapping the products available in the market. In this x-axis and y-axis, there are 4 quadrants. We place the available products in different quadrants, and then we generate the gap between the available products and the customer needs. This is done, compares customers' perception of available products and identifies gap in market, and finally then we will come up with benchmarking. Get the best product available in the market, identify the best product which is available in the market, base performance specifications for new product on this highly sought after product. And reverse engineering, the meaning of reverse engineering is dismantle and inspect the competitors' products. Competitors, good products are taken and they are dismantled. What has gone into the product is seen clearly by the research and development department of our company, and select the features to incorporate into the new product, and this is done through reverse engineering. So, we have discussed perceptual mapping, benchmarking, and reverse engineering, which are the sources of designing the product. Feasibility study, and after the idea generation, feasibility study is performed. Performance specifications are decided. Demand for the proposed product is how much, that is also seen. Cost of developing and producing the product, that is manufacturing the product, is also seen. What is it? And does company have manufacturing capability to manufacture the product? Skilled personnel, whether they are available in the company or not. All these questions are answered while making the feasibility study, whether it is feasible to introduce the new product or not. Then comes the 3 functional areas: form design, functional design, and production design. Under form design, we generate through revising and testing prototypes. Functional design, we design the specifications as far as the design is concerned, and production design gives us the manufacturing specification based on the available machinery with us, and this gives us a preliminary design of the product. Form design means physical appearance of the product, how does it look like. Functional design means performance of the product, and production design, how to manufacture product. And then comes the pilot run and the final tests. Final design and process plans are made through this process. Prototype produced, adjustments made. If some changes are required, changes are made, and the final specifications are agreed. And product is launched in the market. Manufacturing process commences, product is marketed by buying public. It is given to the customers, and our product is launched. Now, this slide shows the difference between concurrent engineering process and the traditional process. Traditional process is linear in sense. Linear in sense means first the customers gives some idea about the product and the product concept is formed. Then it goes to the marketing personnel, and then it goes to the performance specifications, and one after the other all these steps are taken. So, it is a long process, but when we talk about concurrent engineering, all these people sit together and design the product as a team work, as a team collaboration. When we say concurrent engineering, it is a team collaboration and the time is saved. Why concurrent engineering now? Because pace of market change has increased, we do not have time to waste. So, everything is done simultaneously and the time is saved. Companies must keep pace with changing markets. Decisions made sooner rather than later eliminates repetition of tasks, reduces waste and reworking of design, and product quicker to the market. Product is given quickly to the market without wasting time, because everyone is working simultaneously and the problems are solved parallelly. Maximizes company's profit. Company operates more efficiently. That is why this concurrent engineering is preferred over traditional process. To make decision concurrently, team knows the design, goals and the objectives. Team is aware of the interrelationships between all aspects of the design process. Superior communication between all sections of the company, and method is known as quality function deployment, QFD. QFD has come from concurrent engineering only, and now we will discuss QFD also. Quality function deployment is QFD collection of matrices. QFD is nothing but the collection of matrices. Those convert the needs of the customer into technical specifications at all stages of the design and manufacture process. At one stage we say that voice of customer, VOC, at the other stage we say that voice of process. Voice of process is fundamental to the organization. What we have in the company, in the factory, that gives us voice of process, and the voice of customer is given by the customers. Their needs and requirements are voice of customer. We have to match both VOC and VOP. Depending upon the processes available in the company, we take care of the needs of the customers, and how the features are incorporated in the product. We will see the process of making matrices, and this is also known as QFD and house of quality. Product planning. Most popular is the house of quality, which is nothing but QFD. How we make house of quality, I will demonstrate in the next slide, and this is the house of quality. Here we have shown 6 matrices. All these walls, floors, roof, etc. are nothing but the matrices. House of quality or quality function deployment. How these are made, I will just explain. The first one is, number 1 is customer requirements prioritized, scale or percentages are mentioned. So, 1 gives the customer requirements, and number 2 gives a competitive product evaluation. Number 2 is the competitor's product available in the market, and their evaluation is written in the form of the matrix in number 2 position. And next is engineering characteristics, and these are given at the top, and this again is in the form of the matrix. Fourth is interrelationship of 1 and 3 are given in 4 matrix, and relations between engineering characteristics are given in matrix number 5 at the top, tapering roof, and 6 is targets for new product are given at location 6. So, this is the house of quality. This is nothing but the collection of matrices, and these matrices finally give us the features to be added in the product and the processes and the material of construction to be used for the product. And this is very simple and mathematical process. One does not have to think, but only calculations, and you will come up with the material to be used, process to be used, and the features to be incorporated in the product. And nowadays we use Excel software to make the calculations, and the results are in our presence. We see that these are available and we incorporate all those things in the new product. Some facts about QFD. I want to share some of the facts with the viewers. Dr. Mizuno, Professor Emeritus of the Tokyo Institute of Technology, is credited with initiating QFD system. First application of QFD was at Mitsubishi Heavy Industries Limited in Kobe Shipyard, Japan in 1972. QFD was successfully implemented in the production of minivans by Toyota in 1977. A 20% reduction in startup costs was reported in the launch of new van in 1979, a 38% reduction in 1982, and a cumulative 61% in 1984. QFD was introduced in 1984 by Dr. Clausing of Xerox company. Now we will discuss design for manufacture, rather design for manufacturing. Under this, design for anything, say we have design for X, what are the things to be seen when we say DFX? DFX is design for X. X can be replaced with manufacturing, assembly, environment, quality, reliability, etc. A successful design must consider all relevant considerations throughout the life cycle of a product by analyzing the causes and effects of the product. A common set of design guidelines for X includes: X can be replaced by either assembly, environment, manufacturing, quality, reliability, safety, serviceability. So, then we will say quality. When we say for quality, design for quality, design for assembly, design for environment, and similarly design for safety, design for serviceability. And today we shall be discussing design for manufacturing, and this is known as DFM. X is replaced by M, that is why it is design for manufacturing. It is concerned with reducing overall part production cost, minimize complexity of manufacturing. We design the product in such a way that no complicated processes are used in its manufacture. Use common axes and common processes. There should not be tapering axes and number of axes used in manufacturing. We want a limited number of axes be used to manufacture the product. Design for assembly, on the other hand, is DFA, concerned with reducing product assembly cost and making it easier operation to assemble the product. Minimize number and complexity of assembly operations. Individual parts may be more complex in design. Trade-off between DFM and DFA gives us DFMA, design for manufacturing and assembly. If we make the things simple for assembly, this will become difficult for manufacturing. If we make the things simpler for manufacturing, it will make the things complicated for assembly. We have to bring in a trade-off between manufacturing and assembly, and finally we will get a product with a design suitable for manufacturing and assembly. Principles of DFM, DFM guidelines, these are also known as DFM guidelines. There are certain principles which have been devised to make the things easier for manufacturing. Simplify and reduce the number of manufacturing operations. Manufacturing operations be limited. as small as possible and standardize materials and use common parts and common parts available in the market. Most of the products and its assemblies should use the common parts. Design for efficient joining. Finally, we have to join the different parts. There should be efficient methods and procedures for joining also. Open tolerance as far as possible. The strict tolerance etc. must be avoided, and open tolerance must be mentioned on the manufacturing parts. Allow over travel in part design, because in the operations the tools over travel also. We have to give margin for over travel. Avoid special tooling and frequent tool changes. Special tooling is costly and its availability is also poor, so common tools be used in manufacturing process. Select materials for best manufacturability. Use those materials which are easy to handle and easy to manufacture. Specify acceptable surface finish for functionality. Machine for one primary axis whenever possible. And these are some of the guidelines which are used in manufacturing and to make the manufacturing easy. Here I am showing some of the diagrams, and these are regarding grooves. How the grooves be designed so that manufacturing is very easy. I am showing 3 diagrams. Consider degree of difficulty in cutting grooves. So, we have to make the design in such a way that cutting of grooves is simpler. Use as big a radius as possible in corners. Sharp edges are difficult to cut and keep uniform. So, 3 diagrams are shown, and these are the examples of grooves, and grooves be such that they are easily manufactured, easily made. Similarly, holes are there. In the manufactured product, we have to have holes. For these holes, we have to design the holes in such a way that we are able to manufacture these parts with the holes without having any complex process or difficult process. The fundamental rule is keep L by D ratio less than 3 whenever possible. L is length and D is the diameter of the hole. L by D must be less than 3 whenever possible, and do not specify holes that turn corners. So, whenever the holes are there with the corners, those should be avoided. Only straight holes be there in the design, because straight holes are easy to make and manufacture. Plastic injection molding. Minimize wall thickness variation. There should not be lot of variation in the wall thickness, because if the wall thickness is there, it will create warping of the parts and the manufactured products will not be acceptable. Minimize wall thickness variation to allow for uniform cooling rate, otherwise we will have warped parts. And features should be on top or sides of part to allow ease of forming. And then consider molding plus machining as an option. So, these are certain things which must be taken care of while using plastic injection molding. Gathering DFM information, sketches, drawings, product specifications and design alternatives. These are 4 things which are required. The first one is sketches. Sketches must be available for the design of the product and its parts. And the drawing should also be available. When the drawing is available, it clearly shows the dimensions of the product. Material of construction is also written on the drawing. All the dimensions and the tolerances are given, and the surface finish required is also given on the drawing. If the drawing is available, then it becomes easier to decide the process of manufacturing, and the time required for manufacturing a product can also be calculated. Product specification should also be known to the manufacturing people. And then finally, design alternatives should also be given to the manufacturing people. Based on these alternatives and the processes available in the company, manufacturing department will decide which alternative is best to manufacture. A detailed understanding of production and assembly processes should also be given along with the design of the product, because when we manufacture, then we have to assemble the product also. Manufacturing process along with the assembly process is given. Then one is clear about the product, how to manufacture and assemble it, how much time will be there to manufacture it, how much time to be used in assembling the product. Estimates of manufacturing costs, production volumes should also be given. One can decide what is the break-even point which will give us the minimum production. Above that, the profit will start generating. So, for break-even analysis, we need to have the costs involved in the process of manufacturing. Under the DFM method, design for manufacturing, estimate the manufacturing costs. Alternatives are available and we have to decide which alternative to be used based on the manufacturing costs. Reduce the costs of components, and finally, we have to process the map and see where we can reduce the operations to reduce the manufacturing cost. Reduce the cost of assembly also. Reduce the cost of supporting production. Support services and their use should be minimized in manufacturing process. Consider the impact of DFM decisions on other factors, and that is to be seen clearly. Now, we will see how the manufacturing costs are estimated. In this diagram, we have shown the manufacturing system. What are the inputs to this manufacturing system and what are the outputs? Output definitely is the finished product, and one more output is also attached to the manufacturing system, and that is the waste. Two things come out of the manufacturing system. One is the finished product, other is the waste generated. Of course, we want that waste generation must be minimum, and the product and the finished product should be a quality product so that it is accepted by the customer. As far as the inputs are concerned, at the top we have shown equipment, information and tooling. Equipment required to manufacture the product, information regarding the processes and how to use the equipment, and the tooling required to operate the machines and the equipment. All these are the inputs as far as the machinery is concerned. On the left hand side, again we have shown three things: raw materials, labor and purchased components. Raw material, which is required to manufacture the product, manpower required to manufacture the product, sub-assemblies and the standardized parts which are required to manufacture the products. Again, these are input to the manufacturing system. At the bottom, we have attached services required for manufacturing system, energy, power which is required to run the plant and the machinery. It is part of the manufacturing system, supplies and the services. All these inputs through the transformation process in the manufacturing system give us the output in the form of finished product which will be handed over to the customers. A waste is also generated along with the finished product. Idea is to minimize the generation of waste and maximize the finished product. Manufacturing costs defined. Sum of all these expenditures, all these costs for the inputs of the system, that is purchased components, energy, raw material, etc., and for disposal of wastes produced by the system is the total cost for manufacturing. And there are elements of the manufacturing cost of a product. What are these elements? Start with the manufacturing cost under three headings: components, assembly, and the overhead. Under the components, standard components and the custom built components. Under the custom made components, we have given raw material and the processing and the tooling, and this is the component part. In the middle, we have shown the assembly, manpower requirement for doing the assembly and the equipment and tooling required for assembly, and overheads to supervise the entire process, support and indirect allocation. All these costs when put together gives us the cost of the product. Manufacturing cost of a product. Component cost, part of the product. Parts purchased from supplier. Custom parts made in the manufacturer's own plant or by suppliers according to the manufacturer's design specifications. Assembly cost, labor, equipment and tooling required for assembly. Overheads, all other costs like support costs, material handling equipment, quality assurance, purchasing, shipping, receiving and facilities, etc. Indirect allocations not directly linked to the particular product, but must be paid for to be in the business, and these are support costs. Fixed costs and then variable costs are there. Fixed costs are there which are incurred in a predetermined amount regardless of number of units to be produced. That is setting up the factory, work area or cost of an injection mold. These are the fixed costs. Variable costs like incurred in direct proportion to the number of units to be produced, like cost of raw material, etc. Fixed cost and variable costs. Reduce the cost of components. How to reduce? Understand the process constraints and cost drivers. Items which are increasing the cost should be looked into thoroughly and their cost be reduced. Redesign components to eliminate processing steps. Choose the appropriate economic scale for the part process. Standardized components and processes adhere to black box component procurement. What is black box? Black box is only purpose of the component is given to the supplier and the supplier design the product for you. When you give the design, it makes the things complicated and the charges will be very high. Let it be a black box and the supplier may design the product for you. Understand the process constraints and the cost drivers. Redesign costly parts with the same performance while avoiding high manufacturing costs. Work closely with design engineers, raise awareness of difficult operations and high costs, and then come up with a design which uses less cost to manufacture. Redesign components to eliminate processing steps. Reduce the number of steps of the production process and will usually result in reduced costs. Eliminate unnecessary steps. Use substitution steps where applicable. Analysis tool, process flow chart and value stream mapping must be done to reduce the cost of manufacturing. Choose the appropriate economic scale for the part process. Economies of scale. As production volume increases, manufacturing costs usually decrease. So, we have to understand the economies of scale, and we should use this concept to reduce the manufacturing cost. Fixed cost divided among more units will reduce the overall cost of the product. Variable costs are lower since the firm can use more efficient processes and equipment. Even more efficient technologies can also be used to manufacture the product to reduce the manufacturing cost. Standardized components and processes. Economies of scale, the unit cost of a component decreases as the production volume increases, and similarly standard components be used common to more than one product. Analysis tools, group technology and mass customization should be used to reduce the manufacturing cost. Adhere to black box component procurement. As already discussed, black box only give description of what the component has to do or perform, not how to achieve it, how to manufacture it. Successful black box design requires clear definition of the functions, interfaces and interactions of each component. Now, we will discuss design for assembly. So far, we have discussed quality function deployment, concurrent engineering and design for manufacturing. Now, we will devote some time on design for assembly. We have to see that the parts are designed in such a way that the assembly is very easy. Easy operations, less manpower, easy tools are used, no complicated processes for assembly are used. Design for assembly. The aim of design for assembly, DFA, we started with DFX, X can be replaced by M. If it is replaced by M, then it is known as design for manufacturing. When it is replaced by A, this is called design for assembly. So, the aim of design for assembly is to simplify the product so that the cost of assembly is reduced. However, consequences of applying DFA usually include improved quality and reliability and a reduction in production, equipment and part inventory. These secondary benefits often outweigh the cost reductions in the assembly. Here there are certain things to be seen while we are designing the product for easy to assemble. Then the work in process inventory should be reduced, and then this will finally reduce the cost of the product. When we have less inventory, less cost will be incurred for designing, for manufacturing the product. DFA recognizes the need to analyze both the part design, the whole product, and let us assume the part and the product. The complete product is comprising of n number of components, n can be 100, n can be 200 also. So, each component should be designed such that final assembly of the product becomes easy, because each component is to be assembled to become part of the product which is required by the customer. For any assembly, problems early in the design process can be checked. DFA may be defined as a process for improving product design for easy and low cost assembly, focusing on functionality and on assemblability concurrently. We have to see simultaneously functionality of the component and the product and its assemblability, because we cannot compromise with the functionality of the component at the cost of assembly. At one stage, we are making the assembly operations easy, but if we are not able to adhere to the functions of the component, then the easy assembly operation is of no use. So, we have to see both functionality and assemblability together and simultaneously, So, the design is such that its functions are retained and it is easy to assemble. Comparison of assembly methods. Now, we will discuss the certain methods which are used in assembling. Assembly methods can be divided into three major groups, three major categories. Manual assembly, when we carry out the assembly work manually, parts are transferred to workbenches where workers manually assemble the product or components of a product. Here workbench is there or the work table is there where the parts are transported and the worker assemble the parts manually. His workbench is designed such that ease of operation is there. All the components which are to become part of the final product are easily accessible at a distance where hands can pick them up without fatigue and without putting extra energy. And then work tables, work benches are designed and the parts and the components are kept at the relevant places. All the tools used to be used for assembling work are placed at nearby locations only, and the sequence of assembly operation is carried out manually, and this is called manual assembly procedure. Hand tools are generally used to aid the workers in assembling work, and these are available at a approachable distance. Although this is the most flexible and adaptable of assembly methods, there is usually an upper limit to the production volume and the labor costs, including benefits, cases of workers, compensation due to injury, overhead for maintaining a clean atmosphere, healthy environment, etc. are higher. Here we have to see that what is the production rate at which the product is to be manufactured, because the manual operations can handle the quantity to a certain extent only, not beyond that. So, where the lesser production is required, we keep the things manually. When we have manual manpower available, then the cost of that manpower is to be taken into account. Their injury cost and all other costs which are used for employing a worker in the company are to be taken into account, because we are having manual operation and workmen are required for handling that manual operation. Fixed or hard automation. Then we have automatic operations, and I am talking about fixed or hard automation, is characterized by custom built machine that assembles one and only one specific product. Obviously, this type of machinery requires a large capital investment. As production volume increases, the fraction of capital investment compared to the total manufacturing cost decreases. These are specially tailor-made machines which are used for the assembly work for the product. Usually what happens, one machine is designed for one sort of operation only, and such a machine is very costly, lot of investment is required. If the production volume is very high, this high production volume justifies the high investment in procurement of machine which is used for assembling, because the cost of the machine gets divided among the total production volume. Hence, the cost will be reduced because it will be spread over the production volume which is our requirement. If it is very high, it will be spread over a high volume of production. Indexing tables, parts feeders and automatic controls require rigid assembly methods. Sometimes this kind of assembly is called Detroit type assembly. Detroit type of assembly where rigid assembly machines are required. Automatically positioning the components at their standardized locations, and then assembly methods be used. When these are used, these are known as Detroit type of assembly process. Soft automation, earlier we have discussed hard automation, now we will discuss soft automation or robotic assembly methods. And here robots are used to assemble the machines, assemble the components, and this incorporates the use of robotic assembly system. This can take form of a single robot or a multi-station robotic assembly process or robotic assembly cell with all activities simultaneously controlled and coordinated by a PLC or a computer. PLC is programmable logical control. Although this type of assembly method can also have large capital costs, its flexibility often helps offset the expense across many different products. And these robotic methods can be used for a number of products and using them for assembling these number of products. Not like hard automation where a single machine does only single product. Here in soft automation where we are using robots, this system of robots can be used for number of products and the cost can be spread over the number of products, and it becomes slightly cheaper operation when we use robots for assembling the products. And how the costs vary, these are shown in this slide. On x-axis, we are showing annual production volume. Annual production volume is shown on the x-axis. On the y-axis, the assembly cost per product, means per unit product. When it is manual assembly, it is uniform and it is independent. It is not dependent on the production volume. Whatever be the production volume, the assembly cost when it is done manually will remain same. On the other hand, if we use hard automation or soft automation, so automatic assembly or robotic assembly, the cost will get reduced as the volume increases. Automatic assembly lines where hard automation is used, this is directly proportional to the number of products to be made annually, and it is a straight line going downwards. As the volume increases, the assembly cost reduces. When we look into robotic method of assembly, it is a downward trend line, but it is curvilinear line. So, this is the difference between the cost estimation for the three methods. One is manual method, other is automatic assembly, which is hard automation, third robotic assembly procedure, which is soft automation. Relative cost of different assembly methods by type and production volume is shown in this diagram. Design guidelines for manual assembly. So, there are certain guidelines also mentioned to make the assembly procedure simpler and easier. Obviously, the following guidelines depend on the skill of the worker. Eliminate the need for workers to make decisions or adjustments. The assembly should be such that nothing should be left to the worker to take a decision. Ensure accessibility and visibility of the parts of the components. and even the tools also. Eliminate the need for assembly tools and gauges, that is prefer self-locating parts. We will show you what do we mean by self-locating parts in one of the diagrams also. Minimize the number of different parts, use standard parts. Minimize the number of parts, avoid or minimize part orientation. So, parts and the components should be such that their orientation does not have any importance in assembling work. So, avoid or minimize part orientation during assembly, that is prefer symmetrical parts. Prefer easily handled parts that do not tangle or nest within one another. So, that should be the criteria while designing the product for assembly. Note that many products do not lend themselves to these guidelines unless we design them properly. Many such products are sold as ready to assemble kits or require that assembly be shifted to a cheaper labor markets. Design guidelines for hard automation means automatic machines, and there are certain guidelines for them also. The main difference here is that assembly is performed by machines instead of by human manpower. Reduce the number of different components by considering does a part move relatively to other parts. If there is a relative motion between two parts, only then we should have two different components. If there is no relative motion between the two parts, they can be made in one single part also. Must the part be isolated from other parts? Electrical items be isolated from the mechanical items. Items which are having vibrations, those be isolated from other parts. Must the part be separated to allow assembly? Cover plates, etc. should be designed. Use self-aligning and self-locating features. Avoid screws, bolts, etc. wherever possible. Use the largest and most rigid part as the assembly base and fixture. Assembly should be performed in layered bottom-up manner. Use standard components and materials as far as possible. Avoid tangling or nesting parts. Avoid flexible and fragile parts. Avoid parts that require orientation. Orientation-free parts be used. Use parts that can be fed automatically, and design parts with a low center of gravity. There should not be any question of parts being fallen down. Design guidelines for soft automation means robotic assembly lines. Compared to humans, robots are extremely inflexible and stupid. However, they can be programmed to do one thing over and over again with high speed and accuracy. Compared to humans, design the parts so that it is compatible with the robots and effector. Design the parts so that it can be fed in the proper orientation. Minimize part count by incorporating multiple functions into single parts. Modularize multiple parts into single sum assemblies. So, prefer use of modular components. Assemble in open space, not in confined spaces. Never bury important components. Make parts such that it is easy to identify how they should be oriented for insertion. Prefer self-locating parts. Standardize to reduce part variety. Maximize part symmetry. Design in geometric or weight polar properties if non-symmetric in nature. Eliminate tangly parts. Color code, use the color code system for identifying the components and the parts that are different but shaped similarly. Prevent nesting of parts, prefer stacked assemblies. Avoid orienting features on non-symmetries. Design the mating features for easy insertion, provide alignment features also. Insert new parts into an assembly from above, eliminate reorientation of both parts and assemblies, eliminate fasteners, place fasteners away from obstructions, design in fastener access. Deep channel should be sufficiently large enough to give space for use of spanners. Provide flats and uniform fastening and fastening ease. Ensure sufficient space between fasteners and other features for a fastening tool. Prefer easily handled parts. So, viewers, today we have discussed concurrent engineering, doing the processes simultaneously, quality function deployment, house of quality, designing the products in such a way that there is ease of manufacturing, then designing the products such that there is ease of assembly, easy tools are used, manpower fatigue is reduced, production volume is increased, and the efficiency of manufacturing and efficiency of assembly is increased. I hope with this talk the viewers are able to understand the concept of the product design and making it easy as far as manufacturing and assembly is concerned. And the time for launching of the product is reduced, and at the same time cost of launching of the product is also reduced. Thank you so much.
Thank you so much, sir, for this very interesting presentation we had today. And friends, with this, of course, you must take leave, and we are sure that we will be back with the more interesting and informative lectures. So, thank you, friends. Have a great day ahead. Thank you, sir.